It's a joint work with Andrei Shvarevich, and it's a small outline of my talk. At the first, we discuss about a weak limit of our solution. Then we study the different widths of our discontinuities. And for these different widths of our discontinuities, we have two cases. In the first case, we have only smooth shock waves, and in the second case, we have only smooth tangential discontinuities. And in the last part, we talk about smooth weak breaks. So it's our system of gas dynamics. In this system, U is an unknown three-dimensional velocity field. Rho is an unknown function. It's a density. The function P, it's a pressure that depends only from density, and the function P is smooth, and a derivative of P from rho is greater than 0. So, and the coefficients nu0 and mu0 describe the viscosity. So we write the solution of our equation in such form, where S is a smooth scalar function. So we have fast variables there. It's a U, and when our fast variable tends to plus minus infinity, our unknown function tends to its limits U plus minus and rho plus minus. And it's at each moment of time we have a sum manifold that describes such equations. Yes, and this surface is compact. So a little about weak limits of our solutions. When the small parameter epsilon tends to 0, our weak field of our solution has the such form, where tet is a Heaviside function on our surface M, and if the limits of our unknown field is equal, so we have a continuous function ρ0 and u0 that has a such form where index plus, it means that our function equal to 0 inside our surface M, and without index, our function is equal to 0 outside our surface M. So such weak limits we have. As I said, we have two cases. In the first case, we have a width of our discontinuities is of order of our viscosities, and in this case, we have not got a tangential discontinuity. We have only shock waves. It means that the tangential compact of our velocity field U to M does not depend on our fast variables y. And the second case, if our width of smooth discontinuity is of order of roots from the viscosity, and in this case, we have not got shock waves, we have only tangential discontinuity, and it means that the normal component, our velocity field U to our surface M, does not depend on our fast variables y. And in the second case, we have a smooth weak fields discontinuities too. Let's start from the first case. In the first case, we have only smooth shock waves, and for them we have a boundary problem for our limit fields when our fast variables tends to plus minus infinity. we have limits of our field u plus minus and rho plus minus. This system with the Guegueniot conditions like that, and the square brackets denote the jump of our function when we pass through our manifold M. It's our brackets. Yes, and P is a projection into the tangential plane to our surface M. So we have such equation for our profile of a smooth discontinuities. Omega is a scalar function. Functions A and D, it's a known functions from the problem of limiting, vector field. And if we see in the left-hand side of our equation, if this expression have two roots, and between these roots, this expression is greater than 0, then we have a family of solutions. Family of solutions like that. And the function c from xt, it's an arbitrary smooth function on our surface M. And our function c, we write this function from the limit equation of the second approximation, from the following approximation for our equations. From the approximation for u1 plus minus and rho1 plus minus with linearized Guegueniot conditions too. So we can prove the theorem that if the limit problems are solvable, we can write some series for this solution of our equation in such forms. And describing smooth shock waves.
Actually, S describes the smooth discontinuity.
Yes, yes. So the second case, it's a tangential discontinuity. For this case, we have a free boundary problem like that with some conditions. U0, it's a scalar function like that, normal to M component of our velocity field. And if we see on the first equation of the system, this equation means that our motion of our surface M is determined by the velocity field u0. U0, it's a leading part of our asymptotic for the vector field u. So we have a partial differential equation for the profile of our velocity field. This equation is in some difficult form. There is a Lie derivative and covariant gradient and operator of the second quadratic form. It's a projection to the tangent. It's a tangent component to our surface M, and function P and A in this equation has such form. So if we solve this system of equations, we can prove a theorem like a previous case that our solution have some formal series. The last what we discussed now, it's smooth weak breaks. Smooth weak breaks, it means that we have a discontinuity in derivative. In derivative like that. And epsilon tends to 0, 2. So in this case, we have two modes. One mode, it's a hydrodynamic mode, and the second mode, it's an acoustic mode. And the first case, it's maybe some, like a previous case, it's some smooth weak tangential discontinuity, and the second, it is some maybe smooth shock waves. So this statement means that our weak discontinuity propagates along the characteristic of our linearized system of gas dynamics. And it's two types, hydrodynamic and acoustics. And if we solve solution for our limiting fields, we can glue from these fields U plus minus, we can glue the leading part of our asymptotics. So we have the leading part of our asymptotic, and we study the corrections for these asymptotics. Equation for the first corrections. It's a system of equation like that, where omega it's these expressions. So, and if we see on these two equations, and if we write these equations in the vector form, we have some matrix in the left-hand side of these equations, and this matrix is degenerate. So if we have a solution of this system, the right-hand side of our equation may be satisfied the additional conditions, like left-hand side of our equations. So we have two cases. First case, when omega is equal to 0, then we have such equations. And if omega, square omega is a derivative of our smooth function p, then we have such equations. And we have an equation for our profile of the first corrections in some form like that, where U0 it's a scalar product, and the function v it's a projection U0 to the tangent plane to M. So, and we can prove the theorem maybe like previous theorems, that if we solve these equations, we can prove that the solution of our system of gas dynamics, its series have such form, describing a smooth, weak discontinuities.
Discontinuities tangential.
Discontinuities, yes, only for tangential, yes. So, and some conclusions. If our width of discontinuity is of order of viscosity, then there is only shock waves. If the width of our discontinuities is of order roots of viscosity, we have only tangential discontinuity. And for the tangential discontinuity, we can write smooth weak discontinuities too. And these discontinuities is of two types, hydrodynamic modes and acoustic modes. And the weak of discontinuities propagates along the characteristics of linearized system of gas dynamics, in two waves.